Okay, let's dive in. Have you ever been wrestling with a system, maybe something real time?
Yeah, like audio stuff or robotics.
Yeah,
Places where timing is absolutely key.
exactly, where timing is just everything. And you hit these weird glitches, these unexpected pauses, things just hang for a moment.
Happens all the time.
And you're just stuck wondering, is it my code, my application, or is it something like way down deep in the kernel causing the hiccup? It's tough to figure out.
It really is. Finding that root cause can feel like searching for a needle in a haystack, absolutely.
Well, today we're doing a deep dive into a tool that's actually built right into the Linux kernel. It's designed to help find that needle. Uh, Based on the source material we've got, it's called Ftrace.
Ah, yes. Ftrace. Good stuff.
And it has some history, right? The paper mentions it grew out of the latency tracer from the early real-time Linux patch days, the ERT patch.
That's right. Its origins are definitely in trying to solve those really tough real-time latency problems.
So our source material today, it's this really solid technical paper. It focuses specifically on using Ftrace to, you know, zero in on common causes of kernel latency.
Like interrupts being off or preemption disabled.
Exactly. Disabled interrupts, disabled preemption, and also delays in the scheduler itself. Those seem to be the big ones it covers for latency tracing.
The usual suspects.
So our mission for this deep dive is basically to unpack that paper for you, give you the shortcut. We want to make Ftrace make sense, what it is, how you get at its latency features, how to use them, and maybe most importantly, how to actually read the output so you can figure out where your delays are coming from.
And, understanding these kernel level things, it isn't just for kernel developers. If you're doing anything sensitive to performance, could be pro audio, could be industrial controls, maybe just wanting your desktop to feel smooth.
Yeah.
An unexpected kernel pause can just ruin things.
Mhm.
Ftrace gives you the visibility, almost like X-ray vision, to see what the kernel was really doing or maybe not doing right when things went wrong.
Okay, so let's define terms first. When this paper talks about latency, what exactly does it mean in this context?
Good question. Here, it's basically the time gap. The time between when something should have happened in the kernel, like an interrupt firing or a task needing to run,
Right.
and when the kernel actually gets around to processing it. That delay is the latency we're hunting.
And what causes those delays, according to the source?
Well, the paper points out a few main culprits that the Ftrace latency tracers are really good at catching. First, times when interrupts are disabled.
Okay.
That means the CPU just isn't listening to hardware signals or timers. Big source of delay.
Makes sense.
Second, when preemption is disabled, this stops a higher priority task, one that just became ready, from kicking a lower priority task off the CPU.
Ah, okay. Another delay potential.
And third, just plain scheduling latency. Your task is awake, it's ready to run, but it's sitting in the queue waiting for the scheduler to actually put it on a CPU.
Gotcha. Interrupts off, preemption off, waiting for the scheduler.
Those are the main ones Ftrace's latency plugins target. The paper briefly mentions interrupt inversion too, but notes these specific tracers don't directly measure that, though other Ftrace tools might help. So, yeah, focuses on those first three.
All right, so how do you actually, get started? Where do you find Ftrace on a system?
It lives inside the debug's file system. It's a virtual file system like proc or sys.
And that's usually mounted where?
Typically, syskernel debug. If it's not mounted, the paper mentions the command. Mount dbbugs nodev syskernel debug.
Okay, standard mount command.
Yep. And once you're there, you cd into the tracing directory. So syskernel debug tracing, that's the control center.
Right. And inside that directory, the paper lists some important files, available tracers.
That shows you all the tracer plugins you can use.
And tracer.
That's where you tell it which tracer to use.
Then events, trace marker?
Events for event tracing. Trace is where you see the output. Trace marker lets your application write to the trace.
Okay. Tracing max latency and tracing gone.
Tracing max latency shows the worst latency seen so far, and tracing on is the master switch to start and stop all tracing.
So to see the latency tracers, just cat available tracers.
Exactly. You'll see things like ear cough, preempt off, preemptor cough, wake up, the ones the paper focuses on.
An activated one.
Simple echo. Like echo ear cough current tracer. That turns on the ear cough tracer.
Easy enough. And turn it off.
You echo NOP into current tracer. NOP stands for no operation. It basically means no specific plugin is active. Echo NOP current tracer.
Got it. Okay, let's zero in on ear cough first. That measures time when interrupts are disabled. Why is that such a big deal for latency?
Well, think about it. When interrupts are off, the CPU is effectively deaf to the outside world, right?
Mm-hmm.
Your network card finishes receiving a packet, your disk finishes reading data, a crucial timer fires. None of that can signal the CPU. The signal just waits. The longer interrupts are off, the longer that important event gets delayed. That's direct latency.
Okay, that makes total sense. Now, the paper mentioned something about Irkov piggybacking on locked-up infrastructure. What's that connection?
Right. LockDep is another kernel debugging feature. Its main job is to find potential deadlocks by tracking how locks are acquired and released.
Okay.
As part of that, it also happens to track when interrupts are disabled around certain types of locks. The Irksoft tracer cleverly hooks into that part of the LockDep mechanism to know when interrupts are off.
So does that mean I need LockDep fully enabled in my kernel config to use Irsof? Because I hear LockDep can have some overhead.
No, and that's a crucial point the paper makes. You do not need the main LockDep options like config prov locking enabled. Trace just uses the underlying interrupt tracking bits without needing the full, potentially heavier deadlock detection logic.
Yeah.
In fact, the source actually recommends keeping the main LockDep disabled for performance when you're focused on latency tracing with Ftrace.
Good tip. Now, the Heisenberg principle. This kind of blew my mind reading the paper. The idea that just measuring the latency can change the latency.
Oh yeah, the observer effect. It's a fundamental problem in any kind of performance measurement, especially deep kernel tracing.
How does it apply here?
Well, think about the function tracer, config function tracer. If that's compiled in, the kernel potentially puts a little hook at the start of almost every function.
Wow, okay.
Now, config dynamic effect is smart. It makes that hook basically do nothing if no tracer is active. Zero overhead then.
Right.
But if you turn on a tracer like Irkov and the function tracer capability is active, Trace will start recording every single function call that happens while interrupts are disabled.
Which must add up fast.
Hugely. Each function call trace adds a little bit of time, a little bit of overhead.
Yeah.
That overhead makes the section where interrupts are disabled longer than it would be naturally, so the latency of trace reports is inflated.
And the paper's Hackbench example really shows this, doesn't it? Like baseline run, maybe 9.7 seconds.
Yep.
Run with Irksof and function tracing, over 47 seconds runtime, and the max latency jumped to 171 microseconds.
Which is massive. But then run Hackbench with Earsoft, but turn off the function tracing part. Runtime drops to around 34 seconds, and the max latency reported plummets to just 30 microseconds.
Wow. Still some overhead from Irksof itself, but much, much closer to reality. 30 microseconds versus 171. Big difference.
Exactly. It shows how critical managing that tracing overhead is for getting meaningful results.
So how do you turn off that function tracer overhead easily at runtime without needing to recompile the kernel?
There's a handy switch in proc. The paper gives the command echo 0 proxys kernel traceabled. Setting that to 0 disables the function graph and function tracing parts, significantly reducing overhead for the latency tracers.
Okay, echo 0 proxys kernel traceable. Simple enough. Any gotchas?
Just a small one. The source notes, make sure you have a space between the 0 and the me. Some shells get confused otherwise. Echo 0, not echo 0.
Good catch. And after changing that setting,
Yeah.
should you do anything else?
Best practice is to reset the tracer. So echo not current tracer, then echo Irksof current tracer again, or whichever tracer you were using. Just make sure it fully picks up the change.
Makes sense. Okay, so we've got AirTrace set up, maybe disabled function tracing. We ran our test. Now we look at the output file, syskernel debug tracing trace. What are we actually seeing? It looks pretty dense.
It is dense but structured. The paper breaks it down well. You'll first see some header lines, starting with hashtag.
Right.
They give context, hashtag tracer.irkov, the kernel version. But the really important one is hashtag latency, like hashtag latency, 70s. That tells you the maximum duration interrupts were found to be disabled in that trace period, 70 microseconds in this case. That's your worst case scenario caught on this run.
Okay, that's the headline number. What about the entry count, like hashtag 170170?
Yeah, for latency tracers, the numbers often match because each event is just a single max latency record. For other tracers that fill the buffer with many lines, this tells you if the buffer wrapped around. The first number is how many entries got dumped. The second is the buffer size. If it's like hashtag 500100, you know you captured the last 5,000 events, but older ones were overwritten.
Okay. Ring buffer behavior.
Exactly. The header also usually shows info out the task that caused that maximum latency. Something like hashtag task, circ timer 0-5, prio.49 policy.1.
Okay, task name, PID. What about prio and policy?
Policy is the scheduling policy. The paper mentions the codes. Sirhoa 0 is Shibro Normal, the standard Linux scheduler. 1 is Shep FIFO, real-time first in, first out. 2 is Shirmar, real-time round robin. And there are others like batch and idly. So policy.1 means circ timer is a FIFO real-time task.
And prio.49, that's not the usual 199 real-time priority, is it?
No, that's the kernel's internal root prio. Its inverted lower number means higher priority, with 0 being highest. The paper explains the conversion. The user-level priority, 199 you set, becomes 99 user priority internally. So a user priority of 50, which is common for things like circ timer, is 9950 equals 49 internally. That matches the trace.
Okay, internal kernel priority. Got it. Now, below the headers, we get the actual trace lines, columns like CMDO, CPU, sheg, delay time, function A caller. But that flags column, it looks like alphabet soup, 0D or 0D and H1. The paper says this is vital.
Absolutely vital. That little flags column tells you the exact state of the kernel at that point in the trace. Let's break down the characters the paper highlights for latency tracing.
Okay.
First character, interrupts state. D means interrupts are disabled. KE means they're enabled. For error cost, you expect to see D within the critical section being measured.
Makes sense. D for disabled.
Second character, need reschedule flag. N means the kernel wants to do a context switch soon, maybe a higher priority task woke up.
Oh.
Means no reschedule pending. The paper points to an example, line 093, showing N. Tells you why a switch might happen later.
N for need reschedule. Okay.
Third character, interrupt type context. AKH means you're in a hard IRQ handler. AKS means soft IRQ context, or soft keys disabled. H means both hard and soft are disabled. Means both enabled. The paper notes that in RT kernels, soft circuits often run as threads, so S might be less common there.
H for hard key, S for soft.
Okay. Fourth character. This one's super important for locking the preemption disabled depth. It's a counter. If it's a number 1, 2, etc., preemption is disabled to that nesting depth. If it's GAIC, preemption is enabled.
Nesting depth.
Yeah, think of it like this. The kernel enters a critical section, like holding a spin lock, where it can't be preempted. The counter goes to 1. If inside that section it takes another lock that also disables preemption, the counter goes to 2. When it releases a lock, the counter goes down.
Ah, so you can see how deep into non-preemptible code it is. The examples show this right. Line 041 goes to depth 1 after atomic spin lock.
Exactly. And line 046 goes to depth 2 after taking another lock, atomic spin lock or save. Seeing this depth alongside the D for interrupts disabled gives you a really clear picture of why the system was unresponsive. At that moment, it was likely holding locks.
That's really informative. So looking at those example lines, line 020 shows bash entering the timer interrupt.
Yep. Bash 2724 on CPU 0, flag 0 day, depth 0, interrupts disabled, timestamp 1 microsecond, entering SIMPIC timer interrupt. And lines 1811 82 show the end of a context switch into circ timer, name truncated to circtem, flag 010, interrupts disabled, preempt depth 2, timestamp 68s in finished task switch. Shows the scheduler finishing its work while still holding locks.
Okay, the flags and function calls together tell the story. So Urquisoft covers interrupts disabled. The paper mentions preempt off too, measuring time preemption is disabled, but says it's maybe less useful on its own.
Yeah, the reasoning seems to be that often when preemption is off, interrupts might also be off, especially inside spin locks. So just knowing preemption was off doesn't give you the full picture of why a task couldn't run. Was it just preemption, or were interrupts also blocked?
So that leads naturally to the preempt Turtsoff tracer.
Exactly. The paper positions preempt Turtsoff as generally more informative for overall latency. It measures the longest time that either interrupts or preemption, or both really, were disabled consecutively.
Ah, so it's the total time the kernel was essentially hands-off, unable to schedule a waiting high-priority task for either reason.
Precisely. It captures the total duration of that kind of critical section. Its output format looks very similar to Airsoft.
Okay, those tracers cover kernel states being disabled. What about the third type of latency, scheduling latency? The task is ready, interrupts are on, preemption is on, but it's just waiting its turn.
Right. For that, the paper introduces the wake-up and wake-up tracers. Their whole purpose is to measure that gap. From the moment a task becomes runnable, wakes up, until it actually starts executing on a CPU.
Let's start with wake up. How does that one work?
So wake-up tracks the wake-up latency for whatever task is currently the highest priority runnable task in the entire system.
Okay. Seems straightforward.
But there's a really important subtlety the paper points out with a great example. If the task wake-up is currently watching, let's call it task A, wakes up another task, task B, of the same or higher priority. and task B gets scheduled and runs first, the wake-up tracer doesn't switch to task B. It keeps timing until its original target, task A, finally runs.
Oh, wow. So the time reported by wake-up for task A could include time that other tasks were actually running.
Exactly. The paper's example uses hauled and hauled add-on store. Wake-up reported a 150 microsecond latency for hauled add-on store, but looking at the detailed trace with scheduling events enabled,
Let me guess, hold ran first.
you got it. Hauled ran for about 142 microseconds after hauled add-on store woke up, but before it got to run. So hauled add-on store's actual wait time was only about 7-8 microseconds, not the 150 reported by wake-up alone.
That's a huge difference. So wake-up is technically correct by its definition, but potentially misleading about the actual delay experienced by that specific task if you don't see the context.
Precisely, which highlights the importance of enabling scheduling events alongside the wake-up tracer to get the full story.
Ah, events. Let's
Yeah.
talk about those. The paper positions the event tracer as maybe lower overhead than the function tracer.
Definitely. Events aren't a plugin in the same way Irksoff is. They are specific, predefined points in the kernel code, like SCED or candle entry, syscalendar, calmalloc, that can log data when hit.
Yep, you can turn these on independently.
Yes, you can enable specific events or whole groups of events, like all SCED events, and they get recorded into the main trace buffer regardless of what current tracer is set to, even if it's just NOP.
So you could just trace scheduling switches and wake-ups, for example. How do you find and enable them?
You can see what's available with cat available events. They have a system.event name format like sced.scedswitch or irq.software The paper shows two main ways to turn them on/off. One is using the setret file.
How does that work?
You echo event names into it. Echo sced.scedswitch set event enables only that event, overwrites. Echo irk.irkhandle set event adds that event, appends. You can use wildcards too, like echo sched set event to enable all scheduling events, and disable with deck like echo.rq set event, remembering the quotes for the shell.
Okay, set an event for quick changes. What's the other way?
Using the directory structure under syskernel debugged tracing events, there's a directory for each system, sched for arcs, syspels, etc., and inside those, a directory for each event.
Ah, nested directories.
Yep. And each event directory, like events.switch, has an enable file. Echo 1 to enable that specific event, 0 to disable. You can also echo 1 into the system level enable file, event schedulable to turn on all scheduling events, or even events sendable to turn on everything. Probably not recommended.
Right, probably generates way too much data. So the paper shows that even just enabling scheduling events, event schedulable with an op tracer, gives you useful output, right? Like in listing 6.
Absolutely. Just seeing the sched switch and sched wake up events tells you exactly who is running when, who is waking whom up, on which CPU. It's incredibly valuable for understanding basic system behavior and scheduler interaction.
Okay, cool. Now back to the latency tracers wake-up for. Why a separate one just for real-time tasks?
Because of that issue with the regular wake-up tracer potentially getting skewed by other high-priority tasks running first, if you're specifically debugging a real-time application, you really care about the latency experienced by your RT tasks.
Ah, so wake-up trip filters out the noise.
Essentially, yes. It focuses only on tracking the wake-up latency for the highest priority real-time task that's runnable. It gives you a clearer signal for RT performance analysis, less likely to be inflated by non-RT tasks cutting in line.
Got it. Makes sense for RT developers. And the format of those scheduling events we see in the traces, like sched wake-up. The paper shows that line. Bash 6808, 680.120 backtar plus Salzerson 3.0 DAOS migration 0. Can you decode that?
Sure. It breaks down like this. Bash 6808, the task doing the waking, name PID. 6808.120 are its PID, again, its kernel priority, 120, which is normal, and its state, R for running. Plus CO0, the plus means waking, and the 00 is the target CPU, CPU 0, 3.0S. The task being woken, PID 3 is migration 0, its kernel priority is 0, which is max RT prio 99, and its state, S for sleeping, about to wake up.
Okay, so Bash woke up the high priority migration thread for CPU 0. Clear.
And the sched switch format is similar. Sched switch.task old prio old state equals new task.new pid new prio very explicitly shows who's out, who's in, their priorities and states. Combining these gives a really detailed scheduler view.
This is powerful stuff for kernel level issues, but what if the problem isn't just in the kernel? What if my application is doing something weird that triggers the latency, or the latency happens during some app-specific operation?
Yeah.
How does ftrace help bridge that user space-kernel space divide?
That's where trace marker comes in. It's brilliant, really.
The file we mentioned earlier,
Yeah.
syskernel debug tracing trace marker.
Exactly. It's a file that your application can open and write strings to. Whatever you write pops up right in the kernel's ftrace buffer, time-stamped alongside all the kernel events.
So I can literally write starting critical calculation from my C code and see that message interleaved with sked switch and or candle rentry events?
Precisely. You can bracket important sections of your application code with markers like entering function X and exiting function X. Then when you look at the trace, you can see exactly what the kernel was doing or not doing during your critical application phase. It's perfect for correlating application logic with kernel behavior.
That sounds incredibly useful for debugging interactions. But what about those horrible intermittent problems? The glitch that happens once an hour. You can't just sit there staring at cat trace forever.
No, you can't. And the paper describes a really neat trick for exactly this scenario.
Oh,
You set up ftrace with the events or tracers you want, and you make sure tracing is on echo one tracing on. You just leave it running in the background, constantly writing to the ring buffer.
it's always tracing.
Right. Then, in your application code, when you detect the failure condition, maybe a calculation takes way too long, an audio buffer underruns whatever your specific failure is,
Ah,
your application immediately opens the syskernel debug tracing on file and writes a single ASCII character 0 to it.
it writes 0 to tracing on from the application.
Yes. Writing 0 to tracing on stops the trace immediately.
So the application itself acts as the trigger to freeze the trace buffer right when the problem occurs.
Exactly. Because it's a ring buffer, if you let it keep running after the failure, the crucial moments leading up to and during the failure might get overwritten. By stopping it instantly from the application that detected the failure, you preserve that critical snapshot at the end of the trace buffer. It's a fantastic technique for capturing the context of rare events.
That is genuinely clever. Wow. Use the app to capture its own failure context in the kernel trace.
It's a great example of combining user space awareness with kernel tracing power. The paper also briefly mentions the syscall plugin, which is another way to see application kernel interaction. It logs all system calls system-wide into the trace buffer, kind of like Strace, but integrated with ftrace events.
Okay, so bringing this all together, the paper wraps up with that real-world story about the early days of the SART patch and the Jack audio users.
Right, a classic example. They were heavy users of the original latency tracer, and crucially, they didn't just find kernel bugs causing audio dropouts.
They found bugs in Jack itself, too.
Yep. The traces showed that sometimes the latency wasn't the kernel's fault. The Jack application was doing something inefficiently or incorrectly that contributed to the problem. It highlights that latency can come from anywhere: hardware, kernel, application logic.
So you need tools like ftrace to actually dissect where the time is being spent in that whole stack.
Exactly. It gives you the objective data to move beyond guesswork and pinpoint the real bottleneck, whatever it might be.
So let's recap quickly. We've looked at how ftrace, born from real-time needs, helps find latency. We saw Urkos and preemptors off-measure critical kernel off states. We saw wake-up and wake-up tackle scheduler delays with that important wake-up caveat. We covered the power and lower overhead of specific kernel events, and critically, how trace marker and that slick tracing on trick let you pull your application's context right into the kernel trace.
It's a really powerful toolkit. But, looking at those trace examples, especially if you enable lots of events or, heaven forbid, the function tracer temporarily, the sheer volume of data can be overwhelming.
Yeah, thousands, maybe millions of lines.
So it makes you wonder, doesn't it? When you're faced with a really gnarly intermittent latency bug, maybe on a complex production system, how practical is it to just manually read through gigabytes of raw trace? Do you think we absolutely need more sophisticated analysis tools, maybe automated pattern detection or visualization, to really make sense of these huge traces and quickly find the smoking gun? How do we scale the analysis beyond eyeballs on a text file?
That's a really great question to end on. The tooling provides the data, but interpreting it effectively, especially at scale, is a whole other challenge. Food for thought. Well, thank you for joining us on this deep dive into ftrace and hunting kernel latencies. We hope this gave you some solid insights and maybe some new approaches to consider for your own systems.